Principles of Bioproduct Separation, Module 6, Adsorption, Segment 4, Adsorption in a Fixed Bed. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about chemistry of adsorption, batch adsorption, adsorption in a continuous state tank, and in this segment we will discuss about adsorption in a fixed bed. A fixed bed is simply a piece of pipe standing on its end and filled with adsorbent beads. Fluid containing the solid of interest flows into one end of the pipe and out the other end. Initially, most of the solute is adsorbed, so that the solute concentration in the effluent is low, as shown in the figure. As adsorption continues, the effluent's concentration rises slowly at first but then abruptly. When this abrupt rise or breakthrough occurs, the flow is stopped. The adsorbed material is then eluted by washing the bed with water at different pH or with a different solvent. Adsorption in fixed beds is described by four basic equations. The first is a mass balance on the solutes in the liquid as shown in equation 18. The left-hand side represents accumulation in the liquid per differential volume in the bed. The first term on the right-hand side corresponds to the amount of solid flowing in minus flowing out, and the later term on the right-hand side gives the solid transferred from the liquid into the adsorbent. The second term on the right-hand side represents dispersion in the bed. Such dispersion leads to mixing of solute and solvent, even in the absence of any adsorption. In a sense, dispersion is like diffusion. Indeed, the dispersion coefficient has dimensions of length squared per time, like the diffusion coefficient. However, the dispersion coefficient in most fixed beds is much larger than the diffusion coefficient. The second key equation, analogous, is a mass balance on the adsorbed solute as given in equation 19. The adsorption rate R depends on the mechanism responsible for adsorption. This mechanism may be controlled by mass transfer from the bulk solution to the surface of the adsorbent. Alternatively, it may be controlled by diffusion and reaction within the adsorbent particles. It is assumed that the adsorption rate is linear, and the third key equation is shown in equation 20. The fourth and final key equation is an isotherm, as shown in equation 1 until equation 3. The solution is nonlinear and coupled, which must be found numerically. There are four strategies to analyze the data. First, an approximate analysis. Experiments are carried out to develop a breakthrough curve as shown in the previous slide. There are two concentrations in the figure. One, a breakthrough concentration YB, represents the maximum that can be discarded. Second, an exhaustion concentration YE corresponds to a concentration in the eluent when the bed is judged ineffective. The times where these concentrations occur can be used to infer two zones in the bed as shown in the previous slide. First is an equilibrium zone where the bed is essentially saturated. This zone exists from Z equals to 0 to Z equals to L per L minus delta T per TB. Second is adsorption zone. The shape of the breakthrough curve is unaltered as it passes through the bed. The equilibrium zone and adsorption zone contain loaded adsorbents as given by equation 21 and equation 22. Thus, the fraction of the bed which is loaded is given by equation 23. The shorter the adsorption zone, the more completely the bed is loaded. Second, a two-parameter model. The breakthrough curve by two parameters. Second, a characteristic time and a standard deviation. It is assumed that the breakthrough curve shown previously can be described by equation 24. The quantity error function x is the error function of x, and the values are given in the table. Third, a linear absorption model. The third method for analyzing fixed bed consists of solving the basic equations analytically for the case when k equals to ky x strict. The Freundlich isotherm is replaced with the linear approximation. It is also assumed that dispersion is negligible and the fluid in the bed at any given time is small relative to the total volume of the fluid treated, to give equation 25. The fourth method for analyzing absorption in fixed beds replaces a fixed bed with that of a bed moving countercurrently to the solution. If the bed is infinitely long, it can accomplish separations at steady state. The concentrations at the entrance of this infinite bed are in equilibrium. The concentrations at the exit where the solution lives must be zero. A mass balance between the exit and some arbitrary position in the column is given by equation 26. It is assumed that the volume of solution in the fixed bed at any given time is small relative to that treated, and that dispersion is negligible. A steady-state mass balance on the solute is given by equation 27. Dividing by the volume A delta Z and taking the limit as this volume goes to 0 gives equation 28. Equation 27 can be integrated to determine the length of the bed as shown in equation 29. You may want to check these videos on YouTube for a better visualization about absorption. In the next module, we will have a creative presentation. Until then, I am Yusuf from Institut Teknologi Bandung.